So here we go. Check it. I'm going to go for the beastly one first. This one is, I don't know, there's just a lot to think about when you do these types of troth type problems. The, the work involved, of course, there's a pattern to it, so I know you're getting ready to take a test on it. So here's what I can do. I'm going to try and sum it up in the things that I think make sense and see if you can make any sense of it. The weird thing about it is, so if you can remember, here's the big idea. You are adding up an infinite sum of, and that's what an integral does, it adds up an infinite number of something. And what it is thin layers in this tub full of water. And so what I'm doing here in red is like one, infinitely thin, let's say nanoscale thin layer of whatever substance is in that tank, in this case water. And what we do is we add them up at every depth possible. So you can get the idea at the bottom of the tank that, that thin layer of water down there is a different rectangular shape, therefore a different volume down at the bottom there than it is when you get to the top of the tank further up. So what you're doing is you add up all those infinite lengths, and you can't define each rectangle or each volume piece the same way, so you have to have functions that define it. So the way it works is you have to basically find, there's a couple things that play into this, but you have to find the volume of one of those slices. So ultimately what we're going to need, I'm going to draw some pictures of things that we're going to need. We're going to need that. I'm going to try and do 3D. Come on, I can do this. It's tough to draw 3D this time of day. All right, 3D, bam. That's the one we want. And now, here's the thing. The way this one's set up, according to the way the problem is writing it, is that the thickness they want you to do, so if I do the M, these are a couple things that I want to draw, is the end cap and one of those layers of water. And so here's the end cap on the left, and then there's a layer of water there with that dy thing, that rectangle. And the end cap, they're saying put the origin at the center of the bottom of it. I hope I'm reading this right. If it doesn't work when you enter it in, would you let me know? Because maybe I may be misleading you. But here's y-axis, here's the x-axis, and here's the origin at the bottom of the tank. And so that has that does play itself out. So that's an important piece of information. And then there's this, the water. I should do that in blue. What am I thinking? Water is like blue or something. So here we go. Let's go blue. Here we go. There it is. That's the color we wanted. There's our water in the bottom of that tank. And that width of the water across there, that's something we need to find an equation for, because that is the same thing that we're seeing right over here on our rectangular width of our piece, or our water layer across there. If you can look at that, this width here is the same as this width over here. If my drawings don't describe that, I hope those letters do it for you. So take a peek at that for a second, kind of absorb all that. And then the other thing they put in that tank is how long it is. So basically, one of the biggest components is we need the volume of that one slice. We know it's 10 long. Its thickness is dy. It's the infinite. That's the symbol for infinitely thin. So that's an important one. And that width piece, that's going to be a tricky one, because that one is the equation. That's like the big difficulty in this problem, is actually finding the width of that, because it's defined by this trapezoid on the end. And so I'll show you how to set this one up. I hope I do this right, because I kind of haphazardly worked it out. Trapezoids are goofy when you set these up. They require something different. So here's what happens. I'm going to draw all the dimensions in it. You actually have to bust this thing up into a rectangle and two triangles, because they tell you that the width of this in the picture is 3. And they say the bottom width is all of, 1.5? Okay, 1.5. All right. They tell you also that the height is 3 of the whole tank. So take a look at all these drawings. It's like looking at a nasty blueprint. Those are all your big dimensions. And so what we have then is the central width of the water right here is 1.5. So I'm going to zoom way in on this. 1.5. And I'm going to circle stuff. Okay. And then the only thing we don't know is there's this little width here that's an x width, and over here it's the same x width. So I'm going to call it x. Just leave it open like that. We know up here we got some y width. And then over here, Actually, what am I talking about? It's not y width, it's 1.5. This one's up here also 1.5 because it's all proportional, it's a rectangle. Okay, so here's 1.5. These little pieces on the right and left on that top section that I'm looking at, if that's 1.5 in the middle, then what's left on, the left and the right here and here, that has to be, what's left, an equal distribution of what's left to get to 3. So that's 1.5. Both of them have to add 1.5, so that'd be 0.75. 0.75 and 0.75. Hope that all sounds groovy. But ultimately, it has to add to 3. And if the middle section is 1.5, you have to have 0.75 on either side. Okay, so now that we have that, the thing that we have to come up with is some way of defining this width, but it can't be in terms of x. It has to be in terms of y. And the crazy thing is because the way this is oriented and the way the water thickness is, because it's dy thickness, that means all the functions that go inside our integral ultimately have to be in terms of y. So here comes some crazy algebra. This is the part where the brain begins to explode, but if you can hang in there, I think I've got a diagram that'll help. I'm going to redraw that trapezoidal endpoint with stuff, but I'm going to do one more thing to it. Okay, so this is part 2 of the trapezoidal endpoint, or end cap. All right, here it goes. All right, let's put some stuff in it. Got 1.5, and we got 1.5. We're going to get big here, 1.5. What do we say? X, and we said this is 0.75. 0.75. All right, this is I'm going to add a new thing in here that's going to help us. These distance down this blue line right here, the way they're described, remember this is 0, 0 right here, that's 0, 0. And where the water line is some distance y up. And then ultimately the top of the tank is only 3 meters up. And so this top distance right here, that top chunk is going to be 3 minus y. Because if the top is 3, the distance between two things is always measured by subtraction. So if I got y here, and I got 3 up here, if I want to know the distance between them, it's 3 minus y. And that's what we got right there. Okay, that's huge, because that's the same 3 minus y that we're going to put right here on this little triangle. And the reason I do that, and by the way, this is the same y that we put on this triangle here. What I'm looking for is I've got, in my original picture, I had a bunch of descriptions and there were no y's in it. So let me get a new highlighting color because I don't want to mess up what I got. Let's not get putrid green. There we go. This little drawing here had no y's in it. But now I have a way of relating the y's and x's, because whatever it is, I need my equations in my integral to have y's in it. So what you end up doing is coming up with an equation based on a picture that allows you to convert the equation in terms of y. I have a baby crying, so I'm going to call this part 1 of the video, and I'm going to pause it now and